Uh, Hello, welcome back to my YouTube channel. My name is Dosen Pengampu, and today in this video we will discuss about machining process. So my college number is 215531063. So let's start the video. So my video is based on reference that I use is Handbook of Manufacturing Process and How Products, Components and Materials Are Made by James G. Broad, and I use other journal from Google. Okay, in this video we'll discuss about the first one is lathe and other turning operations. The second topic is round hole making methods. Third topic is grinding and abrasive machining. Okay, the first topic we got to go is lathe and other turning operations. So produced with a cutting action, surface of rotation. So the surface having a round or partly round cross the sections. So both external and internal in a workpiece. So the workpiece is rotate, and in a lathe, screw machine or chucking machine, it is held between centers or in a chuck or collect or fastened to a faceplate. The cutting tool is fed into the work or along the work or both to produce a part of the desired shape. So these are several basic types of lathes and relative machines as described below, and many varieties of tools that can be fed against the workpiece. So these machines are used extensively in the product of parts that contains surfaces of rotation. The basic operation performed on lathes are the following. Okay, now in the first topic of lathe and other turning operations, the first subtopic is turning. So it's the most prevalent lathe operations, and its most common form, a single point cutting tool is moved on a precise path with respect to a rotating workpiece. So when the tool moves parallel to the axis of rotation, straight turning takes place, and the surface machine is cylindrical of parts of a cylinder. When the cutting tool moves uniformly closer or further from the axis of rotation as it moves longitudinally, a tapered surface is generated. So this is often accomplished in engine lathe by moving the tailstock supporting center for the work to an off-center positions. So out of alignment with the headstock axis of rotation, these engine lathes, turret lathes, screw machines and chucking machine all perform turning operations to produce all kinds of shafts, axles, spindles, pins, and with the straight of tapered turn surface, these parts as small as wristwatch, shaft, and as large as ocean liner propulsion components are turned on lathes, producing a turned surface of considerably smaller diameter than that of the original workpiece, may involve one or more roughing cuts. So usually with a large depth of cut. So the finishing cuts to produce greater accuracy or smoother surface normally have a small depth of cut. Okay, the second subtopic from lathe and other turning operations is facing. So this facing is produced flat surface whose plane is at right angles to the axis of rotation of the parts. So as the part rotates in the lathe, the cutting tool moves radially towards the axis of rotations. So removing material as it advances, it can also move outward from the center, but the other direction is much more common. So this operation is used to produce flat surface on castings and other parts that usually also require turning or some other lathe operations. Okay, next, the third subtopic from lathe and other turning operation is grooving. So grooving is the cutting tool usually ground to the width and bottom shape required. It's fed into the work cutting a groove of the desired dimensions. So a groove can be cut into any external or internal surface that such as cutting tool can reach. So the internal grooves are usually called recesses. Okay, next is the fourth subtopic from lathe and other turning operation is knurling. So knurling is not really a machining or cutting operations because the knurl is formed, not cut, in the workpiece. So knurling is common lathe or screw machine operation. So the hard knurling tool rolls against the cylindrical surface of the rotating workpiece with high pressure, causing the surface material of the workpiece to flow into peaks and valleys according to pattern of the knurling tool. So the result is a surface in the finished part that is roughened to a particular pattern, useful to improve the grip if the part must be held or rotated by hand when it is used. So several different patterns are possible. Other use for the operation are for decoration and to increase the diameter of the part slightly to facilitate a press fit. So this fifth subtopic from lathe and other turning operation is cutting off or parting. So cutting off is when parts are made in lathes and screw machines from bar stocks. So the final operation is to sever the part from the remaining bar material. This is accomplished by advancing the cut-off tool, a narrow grooving tool, radially into the work. So when the cutting edge advances to the axis of rotation of the part is severed and falls to the bed of the machine. Some machines which make blanks for further machining or other operations are designed to perform only cut-off operation, and other simple ones on a bar and tubular stocks. Okay, we're going to the second subtopic from lathe and other turning operations is engine lathe. So are generally purpose machine that provide the most basic means of performing turning, facing, grooving, knurling, and threading operations. These machines can also drill, ream, and bore holes at the center of their rotations. A typical engine lathe has a chuck or collet to hold the workpiece, and a power rotating spindle and a bed that normally consists of the two ways. A tailstock holds the end of the workpiece opposite the spindle if the workpiece is long enough to require support at the end. A drill, reamer, or other tool can also be mounted in the tailstock so that holes can be machined at the axis of rotation of the workpiece. So other cutting tools, usually single point, are positions in the compound rest and cross slide that are mounted on a carriage that can move in actual direction along the bed of the lathe. So the ways of the bed are machined to be smooth and precisely in line with the spindle. So transverse movement of the tool is provided by the cross slide or the compound rest. The compound rest can be placed at an angle for short taper turning or for angle facing cuts. In this case, in all cases, the movement of the cutting tool can be precisely controlled with machine screws, mostly with manual crank actuation. So still in the engine lathes topic, now we move on to turret lathes, which is different from engine lathes in that they have a slide carrying a usually hexagonal tool holder. It's called a turret. In place of all tailstock, the turret can hold cutting tools in each of its sides and can be fed and on some machines transversely. The turret lathes are therefore adapted for production work. They are particularly suited for moderate production levels when automatic screw or chucking machines may not be justifiable. But when the turret lathes tooling arrangement permits more rapid production than is feasible with engine lathes. So the spindle of machines intended for machining of bar stock are equipped with collar chucks. So when the other components are to be machined, the spindle are fit with chuck jaws suitable for gripping the workpiece. So when the turret lathe is set up for particular operation, retraction of the turret automatically indexed it and position the cutting tool required so that it is in place for the next operations. So fits can be automatic or manually operation to preset stops. Turret lathes generally have a 4 sides turret on the cross slide of the machine. Okay, now the screw machines are automatically lathes originally developed for the mass production of screws from bar stock, but long since used for a wide variety of parts from bar stock over a broad size range. Once it's set up, these machines run completely automatically, and it is common practice for one operator to run a bank of such machines. Machines are available for production parts from bar stocks as large as 8 or we can convert to 200 mm in diameter, but most work is performed on machines capable of processing bar of 2 in 50 mm diameter or even less. So for our next subtopic, we got single spindle screw machines. So these are 2 common varieties of single spindle screw machines: the brown and sharp or turret type and the Swiss type. So the brown and sharp type is essentially an automatic turret lathe. Typically, it has a 6 sides turret mount vertically on a ram, a cross slide on which 2 tools holders can be placed, and 1 or 2 upper tool slides mount near the spindle. So the cutting tools on these holders are moved to machine the bar as it rotates. So the bar is held in a spring collar in the spindle. All motion of these devices are controlled by cams. With the proper cams and setups, the machines will operate fully automatically. So the bar stock is fed to automatically through the hollow spindle. After each piece is cut off, the operation therefore continually repeats, and additional bars can be fed automatically from a magazine attachment. These machines are no longer manufactured, having been replaced by machines whose tool and stock movements are actuated by computer numerically controlled servo motors rather than cams. However, very many of these cam-operated machines are still in use throughout the world. Okay, next is Swiss type screw machines. In the Swiss type machines, tools are mounted on 2 cross slides and 3 upper slides, arranged radially around the spindle. So the headstock holding the rotating bar can slide on the machine's ways. Tool movement are controlled by cams. So tools fit radially to the center of rotation of the bar. So rocker arms driven by cams provide the approach and in-deep motions for the upper tools. So feet are made by shifting the headstock rather than tool slides, and again by cam control. Single point cutting tools are normally used on all slides. Suicide machines were originally developed for clock and watch manufacture and are particularly suited for small shaft and other very small parts. Most current design of Swiss-type screw machines utilize CNC with servo or stepping motors instead of cams to provide tool and headstock motions. So next is multiple spindle screw machines. So the spindle all rotate and then index to a new position after each cutting sequence. There is the tool slide in line with each spindle and often a cross slide for each spindle positions. So all spindle and tool slide motion are automatic and controlled by cams or servo motors. Bar stock is fed at one spindle positions, and some machines are equipped to stop the rotation of the spindle and to perform milling and transverse drilling operation on the workpiece. So the production's rate of multiple spindle machines is considerably faster than that on a single spindle machines because the operation are almost all performed simultaneously, and at each of the other positions, one or more operations are performed on the workpiece. The machine are then designed multiple spindle automatic chucking machines. So next is chucking machines, which are automatic lathes designed for operation on casting, forgings and other parts rather than or bar stock. Mechanism or other features are similar to those of screw machines except for the bar feeding system. Instead, chucking machines have means at the spindle for holding the part to be machined. Special chuck jaws usually must be made to hold the workpiece if its shape is at all irregular. Most chucking machines are single spindle, but multiple spindle machines are also widely used. While the multiple spindle chucking machine have one more spindle locations where our spindle rotation stop for loading and unloading workpiece, which is chucking machines are made for various size of workpiece, ranging up to above 50 lb to 23 kg for vertical spindle machines. Most horizontal spindle machines are workpiece under the 4.5 kg. So now we're going to the second topic from the videos is round hole making methods. The first one we're gonna discuss is drilling, which is the most common tool for drilling. Is a twist drill. Is a rod with helical flutes and two or more cutting edge at the end. It is rotate about its axis and fed actually into the work as it advances to produce or enlarge a round hole in the workpiece. So the chips are carried away from the hole by flutes in the drill. When drilling an actual hole with lathe, the workpiece rotates rather than the drill. So there are other types of drills that may not have helical flutes. Other may have only one cutting edge. The drilling process is very common and is used with a wide variety of machines, ranging from the most sophisticated computer control or multiple spindle machine to handheld electric or crank-driven drills. The most common diameter range for drill holes is about 1.1 to 8 inch, where we can convert it to 3 mm to 11/2 or 38 mm, although diameters from 0.001 or 0.025 mm to 6 inch, which is 150 mm, can be drilled with commercially available special drills. So in drilling two have subtopic. The first one is counter boring. So counter boring is enlarge a hole for part of its depth, and usually machines a flat bottom in the enlarged portions. The operation is most often performed to provide clearance for a bolt head or multi-diameter parts. The rotating cutter is guided by a pilot that fits into the existing hole, so that the counterbore surface is concentric with the original hole. A multi-diameter counterboring tool can produce step counterbores. A counterboring tool in a view, the first one is, and the counterbore hole it produced in a view. The second is the tool can also be produced sport facing, as shown is in the view C. Okay, the second subtopic of drilling is countersinking. It is an operation that adds comfort at the entry end of the hole. A rotating cutting tool with the edge set to the angle of chamfer desired is fed into the hole and removes material at the edge. The tool is centered by the hole, therefore the chamfer is concentric with the hole exist. The operation is typically used to remove burrs or a sharp edge at the end of the hole, or to provide space for a tapered screw head or other tapered object. Okay, the third subtopic from drilling is reaming, which is a secondary machining operation for existing holes. It can provide a more accurate diameter and improve straightness, and a smoother surface finish as it's slightly enlarged the hole. A rotating tool or reamer is used. The operation can be performed on a drill press or other drilling machine, and is something done by hand. Reamers normally remove 0.005 to 0.015 inch, or we can convert is to 0.13 to 0.38 millimeters of diameters. And the reamers normally float, that is, they follow the direction and location of the existing hole, but they can also be guided by bushing to slightly improve the hole's direction or locations. The operation is most common with holes from 1/8 to 11/4 inch. We can convert to 3 to 32 millimeters in diameters. But both smaller and larger hole can be reamed. Taper reamers are used for finishing tapered holes. So the fourth subtopic from drilling is boring. So boring is an operation that enlarges and improves the accuracy of an existing hole. Either the work or the cutting tool rotates about the center axis of the hole. The single point tool describes a circle, removing material from the surface of the existing hole as it advances, enlarging the hole, normally increasing the precision of any number of factors. There are its location, diameter, direction, cylindricity, and finish. And this operation is performed on a boring machine The workpiece is stationary and the cutting tools rotates when performed on a lathe. The workpiece rotates on a lathe, so the operation can then be considered to be internal turning. So the tool spindle and the workpiece holder must be rigid enough to provide the desired accuracy in the bored hole. The operation is performed on holes from about 1.1 per 4 inch or 6 mm in diameter, and larger but is more common or larger holes, especially those too large to be drilled accurately, and for the machining of cast or forge large holes. So in boring 2 we have subtopic. The first one is jig boring and is performed on jig boring machines, which are vertical boring machines of very accuracy. The table movement is extremely accurate and the spindle bearings are very precisely made. The machines are mainly used for making jigs, jates, dies, and fixtures, especially where accurate layout and hole location are essentials. So the second subtopic from boring is horizontal boring mills, are basically larger horizontal milling machines capable of performing boring, milling, and other machining operation on large and often complex parts. And these units are sometimes called horizontal boring and milling machines. The table can move in X and Y direction. And some machines have a table that also swivels. The headstocks that holds the spindle can be raised or lowered. The tool holding spindle can move inward or outward. So these machines are used in the machining of large components that have horizontal holes requiring the precision that boring provides. The machines normally include an end support column opposite the spindle for long boring bars. Tolerance with the machines can be as low as 1 or 2/10,000 of inch. So the third subtopic from boring is vertical boring mills, which are machines with a horizontal table rotating on a vertical axis, and the precision tool head, which is often two tool heads, capable of movement up and down and side to side, in and out radially. And there are maybe more than one across slide with tool holding capability. This machine can be considered to be a large lathe turn on the end. They are especially suited to boring and other operation on parts too large for conventional lathe. Workpieces are typically round and heavy with large diameter and shorter length, and the workpiece is clamped to the rotating table, which can be large as 40 feet or 12 meters in diameter. So both boring and facing are possible. There is no spindle for milling cutters, so all cutting is by single point tools. So the fifth subtopic from drilling is gun drilling, which is a rotating single flute drill. Normally carbide tip is guided by a bushing at the start of the drill hole, and itself guided thereafter by a bearing surface opposite the cutting edge. So a hole through the whole length of the drill provides a means for oil coolant to flow at high pressure to the cutting edge and to flush chips from the hole. Deep straight holes are possible with the process which we originally developed for manufacture of gun barrels. Hole depths of over 250 times diameter are possible. Okay, we're going to sixth subtopic from drilling is trepanning. So trepanning makes a circular groove in a workpiece through the use of one or more cutters or cutting teeth rotating about a central axis, If the grooves are cut all the way through the workpiece, a hole is created, and a circular center piece, called slug, is produced. The process is used primarily for large, so shallow holes. So it is also used the machine round disc from flat stock. Its deep hole trappening is similar to gun drilling. In the forced lubrications is used. The drill is self-piloting and special drilling machines are employed. It differs in that center slug is produced. Okay, the subtopic 7 from round hole making methods is multiple spindle drilling. So when production quantities are sufficiently large, it may be justifiable to construct a drilling head with a number of drills, all of which are driven from the same power source and make contact with the workpiece at the same time. So drilling a number of holes simultaneously, there are three basic types of multiple spindle drill heads: adjustable, geared, and gearless. The adjustable variety use universal joints so that the drill's position can be varied and are desirable for moderate size lots. For higher production and greater precisions of hole location, the gear variety are preferable. The gearless type allows close spacing of the drill holes. Okay, now we're heading to the last topic of the video is the grinding and abrasive machining, which is the grinding and abrasive machining is at the point where the cutting takes place. Grinding is very similar to other machining operation, and the difference is being that the workpiece is cut by the sharp edge of a small piece of abrasive material rather than the edge of the hardened steel or carbide cutting tool. The irregularly shaped abrasive particles may be bound to a wheel or coat belt, or may be loosed. The particle commonly consists of aluminium oxide, silicon carbide, cubic boron nitride, diamond, or other hard materials. The individual abrasive grains are each smaller than conventional metalworking cutting tool, and the grains on a typical wheel make a multitude of. Okay, the first subtopic from grinding and abrasive machining is cylindrical grinding. So cylindrical grinding is used to produce external cylindrical surface by removing materials, creating smoother surface, and providing some precise dimension. In all such operation, both the grinding wheel and the work rotate. The grinding wheel moves towards the workpiece to contact it and away from the work after the grinding is complete. However, in many cases, the wheel also traverse the work or vice versa. There are two basic methods for grinding the surface of components such as shaft, axles, cylinders, and rolls: center type grinding and centerless grinding. Okay, we still at cylindrical grinding. The first subtopic is center type cylindrical grinding, which is the grinding wheel normally rotates on an axis parallel to the axis of the workpiece. The wheel and the workpiece contra rotate so that contacting surface move in opposite direction. After the wheel and the work have made the contact, there usually is actual motion between the wheel and the work for the full length of the surface to be ground, plus some overrun. The wheel may also be fed only transversely into workpiece as it rotates. In this case, the wheel has either a flat face or have a foam thrust into it. The ground surface of the workpiece then can have contours, grooves, or whatever shape is thrust into the face of the wheels, if tapered surfaces are desired. Okay, next we got centerless grinding, which is a process for machining cylindrical surface when the workpiece is not held between centers or in a chuck. Instead, the work is supported by work rest blade at the correct height and contained between two wheels. One wheel is the grinding wheel, the other is regulating wheel, and the regulating wheel does not grind. It rotates the workpiece at a constant rate of speed, and the process produces accurate diameters and roundness with smooth surface in parts such as pins, shaft, and rings. Both through feed and in-feed methods can be used, and production can be quite rapid. And the method is normally not applicable if there are flats, keyways, or other. Okay, next we got through feed centerless grinding. In this method, the regulating wheel is can't slightly a flat face or have a foam thrust into it. The ground surface of the workpiece that can have contours, grooves, or whatever shape is thrust into the face of the wheel. If tapered surfaces are desired, the machine is set so the axis of rotating of the work and the wheel are not parallel. Long slender part and other subject to deflection or vibration during grinding may be supported by a steady rest. Okay, next is in-feed centerless grinding, which differs from the through-feed process in that part does not move actually. Stop in the machine prevent actual movement until the part is ejected. Instead, the grinding wheel is fed into the works once the workpiece is positioned. After grinding, the wheel retracts, the part is removed or ejected, and another is inserted. If that grinding wheel is thrust with a foam, that foam is ground into the workpiece. Tapers, multiple diameters, grooves, and other irregularities shapes can be ground so long as the grinding wheel is appropriately thrust. The process is also useful when the portion of the workpiece is larger than the surface to be ground. It is illustrated. Next is end-feed centerless grinding. It's used to tapered parts, either the regulating wheel or the grinding wheel, or both are thrust to provide the desired taper angle. The two wheels on the work rest blade are set in fixed relationship to each other. There is stop to control the position of the workpiece, which is fed and removed actually. Okay, next from grinding and abrasive machining is internal grinding. So it's a process to finish machining existing round holes. It normally is performed on a lathe-like machine. The workpiece is held in a chuck or faceplate, holding fixture and rotate about the axis of the hole to be ground. The rotating spindle carrying the small grinding wheel is inserted into the hole and then fed radially to contact the surface. The wheel can be cylindrical or thrust with foam. If the internal surface to be ground is cylindrical, the wheel is also traversed axially. The diameter control can be maintained by dressing the grinding wheel with a diamond tool in a fixed position with respect to the axis of the hole. Internal grinding is most commonly used finish a machine precision holes in hardened workpiece. Large, heavy parts are internally ground on vertical spindle machines since loading and positioning such parts is easier if the rotary surface is horizontal. If the large workpiece is too bulky or unbalanced, the rotate it is held in a fixed position and then grinding wheel is moved in the planetary motions around the hole's axis, as in jig boring. Okay, next is internal centerless grinding. It can be used to finish machine sleeves, rings, and similar parts. The workpiece is held between three rolls which locate it and provide rotation. The grinding wheel is inserted into the center hole and fed radially to contact the inner surface of the hole, as in regular internal grinding. The process ensures concentricity between the outer diameter of the part and its center hole. It is suited to mass production situation because the part does not have a place in a chuck and handling is simplified. The grinding of bearing raceway is a common application. Sleeves and cylinder liners are also ground by this method. Tapered holes can be ground on some machines that allow the axis of the grinding wheel to be set at an angle of the axis of rotation of the workpiece. Okay, next is surface grinding. Surface grinding moves the workpiece in a horizontal plane so that it passes under a revolving grinding wheel which contacts it and removes surface material. The result is a part with a flat, smooth surface and an accurate thickness or height. Various arrangement of grinding wheels and various table movement methods can be used. The table movement is most often reciprocating, but the rotary table are also common. The wheel spindle may be horizontal or vertical. The latter requires a cup-shaped or segmented wheel, which cuts on its face. The most common method for holding the workpiece is with a magnetic chuck, although holding fixtures and other methods can maybe also be used. Surface grinding is also used to sharpen cutting tools. Okay, next is horizontal spindle surface grinding. A surface grinding with a horizontal grinding wheel spindle. The wheel cuts on the peri-peri. The table may be either circular with the rotational motion or more commonly rectangular with a reciprocating motion. In both arrangements, the wheel advances perpendicularly to the basic direction of motion with each cycle of table movement, and thus generates a flat surface. This approach is used extensively in tool shops to make a reconditioned dies and to produce machine surface on which there are moving parts with a reciprocating table. Horizontal spindle surface grinding can be used to machine slots in hardened workpiece by dressing a form of the grinding wheel, and a ground surface can be given a form rather than a flat surface. Okay, next is vertical spindle surface grinding. It uses a grinding wheel mount on a vertical spindle with either a rotary reciprocating table. Various methods are used to move the wheel across the work. The cup-shaped segmented or cylindrical wheel covers a larger area than the side of the wheel does in a horizontal spindle arrangement, so cross feet of the work table or wheel may not necessary. These machines are typically used in production application while horizontal spindle machines are more common in toolroom or jobbing works. Vertical spindle machines are used in the manufacture of cylinder head surface, gear and pulley face, and other moving parts are required. Flat, smooth surface weldments, casting, and forging are ground on these machines, and this part usually have somewhat liberal tolerance for dimension and surface finish. However, vertical spindle machines have the capability of producing the fine finishes and close tolerance typical of tool room work. Some machines have more than one spindle and thus can do rough and finish grinding in one pass, or can grind several surfaces of the workpiece simultaneously. Okay, now we're heading to third subtopic from grinding and abrasive machining is script fit grinding. So it is an abrasive machining process capable of heavy stock removal. It is particularly applicable to hard materials that would be difficult or unfeasible to machine with milling cutter. The depth of cut normally ranges from 0.20 to 2 millimeters, much more than conventional grinding, but the table speed is low. It's about 1 to 50 centimeters per minute. The process does resemble milling, but the grinding wheel takes the place of the milling cutter. The grinding wheel is soft and made with a very open, porous structure to provide space for flow of cutting fluid. Now the wheel spindle is lowered gradually as the wheel wears. Continuous cross dressing is normally used, and wheels can be dressed with a form if desired. Now the cutting force are high, and the machine must be rigid and capable of closely controlled table speeds, otherwise wild breakage could occur. So we're going to the fourth subtopic from grinding and abrasive machining. So the fourth one is jig grinding. So a jig grinder is a precious vertical spindle machine similar to a jig borer. It is used to internal grinding. It has a horizontal table that can be moved and located very accurately. The spindle head contains a high-speed grinding head that rotates the grinding wheel about its axis, but the axis can also revolve that planetary motion. The head can also move vertically with reciprocating motion, and thus holes can be ground to very accurate locations and diameters. And as the head reciprocates vertically to high levels of cylindricity, the machine is used for finish grinding of hardened dies, molds, jigs, and fixtures. Okay, the fifth subtopic is low stress grinding. So it's a variation conventional grinding in which of the objective is to minimize stress developed in the workpiece by grinding operation. It differs from conventional grinding in that very low wheel in feet or down feet weights. Frequently, grass coarse, softer, open grind wheels and liberal flow of coolant are used. Wheel speed also may be low. Abrasively grains in the grinding wheel should be sharp, and wheels should not be allowed to become loaded. The process is applicable when the part to be ground is subject to high stress in use or is susceptible to damage from heat. Parts made from more materials such as high-strength steels, cobalt alloys, titanium alloys, and high-temperature nickel alloys that are particularly sensitive to surface cracking and residual stresses. From conventional grinding can be finished ground with this approach. Okay, next is plunge grinding. It's simply a center-type grinding operation where there is no transverse feed of grinding wheel. Instead, the wheel is fed directly into the work. If the wheel is dressed with a form, that form is ground into workpiece. If the width of ground area is no more than the width of the wheel, the operation can be referred to as plunge grinding. The term in-feed grinding is also used. Okay, the subtopic 7 from grinding and abrasive machining is disc grinding. It's a means for producing flat surface. The workpiece is held against the flat side face of a large rotating abrasive disc. So the operation can be performed manually when dimensional requirements for the part are not served. In production situation, double disc grinding is sometimes employed. The workpiece is fed between two abrasive discs which grind the opposite surface of the workpiece at the same time, thus controlling flatness, thickness, and parallelism in the same operation. Parallelism and flatness surface is particularly good with this machine because there is no magnetic chuck to pull down non-flat parts, only to have them spring back to non-flat condition after the operation. So double disc grinders are used in the production of automotive connecting rods, disc brake, rotors, compressor vanes, and cast iron rocker arms. So next is abrasive belt grinding. It uses an abrasive coat-cloth belt to remove metal. The endless belt runs between the drive wheel and contact wheel, and the workpiece bears against the belt and the contact wheel. The abrasive grains on the belt are arranged with orientation and spacing to optimize metal removal rates. So the process can provide faster metal removal than grinding with a wheel and is then often referred to as abrasive belt machining. So metal removal rates of 193 cm, which is of belt width, are feasible with standard 4 belts. And this rate is faster than those attainable with milling machines, even under the fastest metal removal conditions. And belts as wide as 10 feet are allowed the entire surface to be ground in one pass. So the process can provide lower heat levels than grinding with an abrasive wheel because the belt carries away heat effectively. Okay, next is abrasive jet machining. So it provides cutting action from the effect of finely powdered abrasive in high velocity stream of gas. Mags of rubber, glass, or copper may be used to help limit the abrasive action. The process can be used for drilling, cutting, etching, trimming, cleaning, and deburring operation on variety of metals that non-metals, especially hard and fragile materials. The process is less suitable for softer materials that may trap the abrasive. Ceramics, glass, silicon, and mica are machined with this method. Sheets of these materials can be cut and drilled. An abrasive jet can produce intricate holes that would not be easily made by other methods. Other applications are making identification of workpiece, trimming and cleaning electronic components, and removing surface coating, including plating. Cutting rates are slower than those achieved with more conventional process, but there is no heat damage to the workpiece. Okay, next is abrasive flow machining or AFM. So uses as viscous putty like abrasive medium which is pumped so that it flows against the workpiece. The abrasive particles in the medium rub against the workpiece, gently removing surface material. So the process is used to round sharp corners, finish edge, remove cast layers from EDM or laser machining, polish surface and remove burrs. AFM is particularly useful when the area being machined is not accessible for other method. In practice, two cylinders on opposite sides of the workpiece are used to contain and pump the medium, which flows back and forth repeatedly through as many as 100 cycles. until sufficient material is removed from the workpiece. Okay, next up we got ultrasonic machining. So until an abrasive in a water slurry and shock tool. With the abrasive between the tool and the workpiece, the tool is vibrate at ultrasonic frequency. The vibration of the tool drives the abrasive particle against the workpiece, cutting a cavity that the same shape as the tool. The frequency of vibration is usually between 19,000 and 25,000 with a low amplitude to 0.0005 to 0.0025. So the abrasive slurry is pumped through the gap between the tool and the work. The gap range from 0.001 to 0.004 inch, and the slots, holes, the cavities of various shapes can be produced in ceramics, glass, carbide, tool steels, honeycomb materials, and gumstones. And holes and cavities can be non-round and curved. Material removal rates are low, but there are no heat effects, no bursts, and surface stress. Our low holes have something inherent, sidewall taper. So in rotary ultrasonic we got the subtopic. The first one is rotary ultrasonic machining, which is used as a rotating tool coated with diamond abrasive and ultrasonically vibrate to machine hard and brittle materials. There is no abrasive slurry but a liquid coolant, usually water, is used milling. Milling, drilling, and threading operation can be performed, but drilling is a primary application. Non-metals, glass, aluminium, ceramic, quartz, sapphire, and composite materials are normally processed. Okay, next is abrasive flow machining, or AFM. So uses as viscous putty like abrasive medium which is pumped so that it flows against the workpiece. The abrasive particles in the medium rub against the workpiece, gently removing surface material. So the process is used to round sharp corners, finish edge, remove recast layers from EDM or laser machining, polish surface, and remove burrs. AFM is particularly useful when the area being machined is not accessible for other method. In practice, two cylinders on opposite sides of the workpiece are used to contain and pump the medium, which flows back and forth repeatedly through as many as 100 cycles until sufficient material is removed from the workpiece. Okay, next up we got ultrasonic machining. So until an abrasive in a water slurry and shock tool. With the abrasive between the tool and the workpiece, the tool is vibrate at ultrasonic frequency. The vibration of the tool drives the abrasive particle against the workpiece, cutting a cavity that the same shape as the tool. The frequency of vibration is usually between 19,000 and 25,000 with a low amplitude to 0.0005 to 0.0025. So the abrasive slurry is pumped through the gap between the tool and the work. The gap range from 0.001 to 0.004 inch, and the slots, holes, the cavities of various shapes can be produced in ceramics, glass, carbide, tool steels, honeycomb materials, and gumstones. And holes and cavities can be non-round and curved. Material removal rates are low, but there are no heat effects, no bursts, and surface stress. Our low holes have something inherent, sidewall taper. So in rotary ultrasonic we got the subtopic. The first one is rotary ultrasonic machining, which is used as a rotating tool coated with diamond abrasive and ultrasonically vibrate to machine hard and brittle materials. There is no abrasive slurry but a liquid coolant, usually water, is used milling. Milling, drilling, and threading operation can be performed, but drilling is a primary application. Non-metals, glass, aluminium, ceramic, quartz, sapphire, and composite materials are normally processed. So that's all for my video. I hope you guys enjoyed the video. Thanks for watching, and we'll see you guys in the next video.